So next, as an application of quotient topology, we will define the Grassmannians. So let us begin. So let G be a group and such that the set G also, such that the underlying set G also has a topology. Right. So we say that G is a topological group if the two maps. So we have, since G is a group, we have the multiplication map, which is x comma y maps to xy. This is the product in the group, and we also have the inverse map, x goes to x inverse. Right? If these two maps are continuous. So this question makes sense because G is also, there's a topology on G, and therefore G cross G has the product topology. So we can ask if both these maps are continuous, and if both these maps are continuous, then we say that, then we call G a topological group. So let's begin by making a few observations about topological groups. First, if G is a topological group, then left translations. So these are the maps LA from G to G. LA of G is defined to be A times G, and right translations. So these are the maps RA from G to G, defined as RA of G is equal to G times A. These are continuous. These are continuous. Right? So let's see why this happens. So we can look at G cross G to G. We have the multiplication map, right? And here we can look at A times G sitting inside G cross G. So this inclusion is given by A comma maps to A comma G, right? And when we multiply, we get AG. So this composite, so this is homeomorphic to G, right? So this composite is LA. So since this inclusion is continuous and multiplication is continuous as G is a topological group, so this implies that LA is continuous. Right? Similarly, we can take G cross A sitting inside G cross G. This is homeomorphic to G, right? And to see that the right translation RA is continuous. Right? So the inverse of LA is, so the left translation is a bijection, and the set theoretic inverse is exactly LA inverse, right? So this implies that LA and RA. So similarly for RA are homeomorphisms. Okay. Similarly, the inverse of I, since the inverse map is a bijection and I square is equal to identity, so this implies that the inverse map is also homeomorphism. So left translations, right translations, and inverse are all homeomorphisms. The next observation we want to make is, let U be the collection of open subsets containing the identity element. Then for A in G, the collection AU. So here AU is equal to the left translate of this set U is the collection of open sets containing A. So clearly, since LA is a homomorphism, LA of U is an open subset and it contains A because the identity is in U. Yeah? And conversely, if we take an open subset W which contains A, so then this will imply that A inverse of W contains E, and since this is equal to LA inverse of W, right? Since LA inverse is a homeomorphism, LA inverse of W is going to be in this collection over here. So therefore A inverse W we can write as A times A inverse of W, right? So therefore even this W is obtained is in this collection. Okay. So similarly, the collection U times A is the collection of, by the same reason, containing the element A. Okay, so let's make this third observation, which is a lemma, which is a very useful lemma. So let V containing identity be an open subset, right? Then there is an open set U which contains the identity such that the set U times U is equal to all those AB with A and B in U. So this is equal to U square, right? So we have U square is going to be contained in V. So given any open set V which contains the identity, we can find a smaller open set U such that U square is contained in V. So for instance, if we take the real line under multiplication, under addition, and we take the neighborhood 0. So if we take an open subset which contains 0, so let's say B 0 epsilon, right? This V, then we can take U to be B 0 epsilon by 2, right? So the multiplication over here is just the addition. So if you take any x comma y in U, then clearly x plus y is in V. Okay. Right. So let's prove this. So consider the multiplication map from G cross G to G. This is the multiplication map. Which is continuous. Right. So this implies that the inverse image of V is an open subset and it contains this element, right? In particular, there is a basic open subset which contains this element and it is contained in M inverse V. So this implies there exists U1 containing E and U2 containing E such that U1 cross U2 is contained in M inverse V. Right? So we just take U to be U1 intersection U2. Right? So then U cross U is contained in M inverse V, which implies that U times U is contained in V. Okay. Okay, so make the fourth observation. Let V be an open set containing an element X in G. Right? So then there exists an open set U which contains the identity such that U is equal to U inverse, and so U inverse is the set of U inverse where U belongs to U, yeah, or equivalently this is I of U. So U is equal to U inverse and U x U is contained in V. So the proof is very similar to the previous lemma. So let's prove this. So proof. So consider the map G cross G cross G to G. Right. So we can first project to the first two coordinates. Okay, sorry, not this is right. This is A comma B comma C maps to AB comma C, which maps to ABC. Right. So this map is continuous. This is easily checked, right? So we restrict it to, so we restrict this to the subspace G cross X cross G. Right? So this composite is then A comma X comma B maps to AXB, right? So this implies that, so let's call this composite map F. This is homeomorphic to G cross G, right? So, so since F is continuous, so this implies that F inverse V is open, right? So again this implies that there exists F inverse V is open and it contains the element identity X identity, right? So this implies that there exists open sets U1 containing identity and U2 containing identity such that U1 cross X cross U2. This X is really playing no role over here, right? So we could have simply considered the map G cross G to G given by A comma B maps to AXB, right? And once we prove that this map is continuous, we can do this entire argument. So is contained in F inverse V, right? So we take U0 to be equal to U1 intersection U2. So we take U0 first. So this will imply that U0 cross X cross U0 is contained in F inverse V, which implies that U0 X U0 is contained in V, right? But U0 may not have the property that U0 inverse may not be equal to U0. right? So to rectify this, we take u to be equal to u naught intersected u naught inverse, which is equal to u naught intersected I of u naught. Right? Since I is a homeomorphism, I of u naught is also an open subset. So both these contain the identity, so the intersection is an open subset which contains identity, right? And it's easily checked that. So then it is easily checked that u is equal to I of u, and obviously u x u is going to be contained. Okay. So now that we have these lemmas in place, we will prove this interesting. Okay, we need one more lemma. Let H be contained in G be a closed subgroup. So what this means is that H is a closed subspace of G in the topology on G, and also H is a subgroup. Okay. So let X be an element which is not in H. Okay. So then there exists U containing identity open such that U is equal to U inverse and U x U intersected H is empty. So let us prove this. Right. So since H is closed and X does not belong to H, right? So this implies there exists an open set V. I mean, we can simply take the complement of H containing X such that V intersected H is empty. Okay. So for this previous lemma that we proved, this lemma, right, this point 4 implies there exists U open which contains identity such that U x U is contained inside V. Right. So this implies that U x U intersected H is empty. Okay. So using these preliminary results, we prove the following proposition. Let H contained in G be a closed subgroup. Right. So then G mod H with the quotient topology is Hausdorff. Right. So let's recall that G mod H is equal to G mod equivalence, where X is equivalent to Y. Every subgroup defines an equivalence relation. X is equivalent to Y if and only if Y inverse X belongs to H. Right. So we have this equivalence relation on G, and G is a topological space. So we can look at G mod equivalence and give it the quotient topology. And our claim is that this space is Hausdorff. So let us prove this. Let's take 2 points in G mod H which are distinct. Right. So be 2 cosets. Right. So then this Y inverse X, it does not belong to H. Right. So choose a neighborhood E of identity open such that U is equal to U inverse and U Y inverse X times U intersected H is empty. So we can do this using the previous lemma, right? So note that this happens. So note that u y inverse x u intersected h is empty if and only if x u h intersected y u h is empty. Okay. So there is an easy set theoretic check. So let's do this. So suppose let's assume this. Let's assume this is empty and prove this, that this intersection is empty. If not, then there is x u1 h, this is equal to y u2 h1 h2, right? This implies that u2 inverse y inverse x u1 is equal to h2 h1 inverse, right? This implies that u, since u2 is in u, u2 inverse is also in u, because u is equal to u inverse, intersection h is not empty, which is a contradiction. Right. So similarly, we can prove the other way. Let's assume this is empty and let's prove this. So if this is not empty, then there is u1 y inverse x u2 is equal to h. So this implies that x u2 is equal to y u1 inverse h, but this implies that x u h intersected y u h is not empty, which is a contradiction. Right. So thus we see that this holds. Okay. So now, if pi from G to G mod H denotes the natural map, then note that pi inverse of pi of x u h is equal to x u h. Right. In fact, one easily checks that. Pi inverse of pi of a is equal to a times h, right? So this is equal to union of h in h, a times h, right? For every subset a containing G, right? So this is an easy check which I will leave it to you, and using this check, so what we will get is this check implies pi inverse of pi of x u h is equal to x u h multiplied with h, right? But h times h is equal to h, since h is a subgroup, so this is just equal to x u h. Okay. So similarly, pi inverse of pi y u h is equal to y u times h. Okay. So now, as x u h, this is equal to union h in h x u h, right? And these sets are open, and right translations by elements of H are homeomorphisms. So each of these sets is open, and we are taking a union of open sets. Right? So this implies that this set is open. Right? Which implies, by the definition of quotient topology, that pi of x u h is an open subset in G mod H which contains XH, this coset, right? Similarly, pi of Y UH is an open subset which contains the coset YH, right? So thus we have our XH here, we have our YH here, we have constructed two open subsets of these two in the quotient topology, and we claim that these are disjoint. We claim that these are disjoint. Right? If not, right? So let's assume they are not disjoint. So what do we have? We have pi of XUH intersected pi of YUH is non-empty, right? Since pi is surjective, that will mean that when we take pi inverse of pi of XUH intersected pi of YUH is non-empty. This implies that pi inverse of pi of XUH intersected pi inverse of pi of YUH is non-empty. So this is non-empty as pi is surjective, right? But this is equal to XUH and this is equal to YUH as we saw, and this intersection is empty, which is a contradiction. Right? So thus these two open neighborhoods and are disjoint. Okay, so this shows that G mod H is Hausdorff. So this completes the proof of the proposition.